Hello everyone. In today's lecture, we will continue working on the design of digital filters. In the previous lecture, we've had an introduction on the design of digital filters, and we've seen that there are two types of digital filters, FIR and IIR. In today's lecture, we will start working on the design of finite impulse response digital filters, or FIR digital filters. This is the kind of filter whose impulse response, h of n, has a finite duration. And the objective is to try to find a system whose frequency response, h of e to the power j omega, approximates the desired frequency response, h desired of e to the power j omega. But before we do so, let me remind you with some equations and facts related to the Z transform and the discrete time Fourier transform and how they are related to each other. So let's move to our whiteboard over here. If you remember from the previous lecture, a digital filter is simply an LTI system with an impulse response h of n, and we need to find this impulse response and find the system transfer function and find the frequency response of a system that would approximate the desired frequency response. So let me remind you, how can we find the system transfer function h of z? We simply use the definition of the Z transform. H of z is defined as the summation of h of n times z to the power minus n for n going from minus infinity to positive infinity. And as you remember, h of n is the impulse response, and h of z is a system transfer function or a system function. And from this system function, we can learn a lot about the system properties, causality, stability, position of poles, and so on, as we have seen in the previous chapter. This is basically the Z transform. So all what we have learned in the previous chapter will be very useful actually in this chapter. We're learning to design the digital filters. And let me remind you also of the fact that if you set modulus z, which is r, if you remember, z is a complex variable with a magnitude r and angle omega. So it's usually written in the form r e to the power j omega. So if we set r to be equal to 1, which is basically going along or around the unit circle, in this case, z becomes simply e to the power j omega. And now, if we go back to this expression of h of z, if we replace z by e to the power j omega, we will get h of e to the power j omega, which is the frequency response of the system. So, h of e to the power j omega will be equal to summation over n going from minus infinity to positive infinity, h of n e to the negative j omega n. And this is basically the definition of the discrete time Fourier transform. So now in this equation we're computing the discrete time Fourier transform of the impulse response. H of n is the impulse response. And the quantity computed over here, h of e to the power j omega, is known as the frequency response. Frequency response of the filter we are designing, be it a low pass or high pass and so on. So up till now there is nothing new. We are just reminding you guys of Z transform and its relation to the discrete time Fourier transform. Now, if you want to compute the inverse discrete time Fourier transform, what is that? In this equation, we have h of n, and we need to compute the frequency response. This is called the discrete time Fourier transform. If you want to do the inverse discrete time Fourier transform, you start with a frequency response. and then you need to find the impulse response. And the equation goes like this: h of n is equal to 1 over 2 pi integration from minus pi to pi h of e to the power j omega times e to the power j omega n d omega. And this is basically the definition of the inverse discrete time Fourier transform. This equation is very important and I'm going to use it a lot in this chat. So why are we performing the integration only from minus pi to positive pi? If you remember, in the previous lecture we had a supplemental video in which we discussed the spectrum of discrete time signals, and we've seen that if we have a discrete time signal and we're using the normalized frequency lowercase omega, the spectrum becomes periodic every 2 pi. So whatever is happening in this interval from 0 to 2 pi will be repeating itself from minus 2 pi to 0, from minus 4 pi to minus 2 pi, and so on. It's kind of periodic. That's why we are only interested in defining the function h of e to the power j omega, the frequency response, over one cycle, one fundamental period, and whatever is happening in this period will be repeated for the remaining part of the frequency up to infinity. So that's why we are interested only in the range from 0 to 2 pi or from minus pi to pi, any cycle of the length of 2 pi. That's why the integration over here is happening from minus pi to pi, because this is a fundamental period, or we can do it also from 0 to 2 pi, it's the same. That's why, because it's a fundamental period and the frequency response h e to the power j omega is only defined over this range. Okay, so now let's go back to our slides and start talking about the design of FIR digital filters. In this lecture, we will talk about designing FIR filters with linear phase. Linear phase is a very important feature of a filter. If you remember in the previous lecture, we have said that the phase response is either left completely unspecified or it's required to be linear. And today we are talking about the case where there is a requirement to design a filter with linear phase. But the first part here is trying to answer the question, why do we need linear phase? Why do we want a filter with a linear phase? But due to the limited time we have, I will skip this part right away. So from slide 2 up to slide 6, we will not be discussing this part right now. I will move right away to designing FIR filters with linear phase. Okay, so now, what do we mean by a linear phase? Let's see. So, consider an ideal low-pass filter with a linear phase. So, for an ideal low-pass filter, the frequency response would look like this. If this is omega, let's try to plot h of e to the power j omega. And as you know, in general, the frequency response h of e to the power j omega is a complex number. That's why we will be plotting the magnitude and the phase. So we will have two plots over here, one for the magnitude and the other one for the phase. Okay, so first part for the magnitude, it's a low-pass filter, so it will allow the lower frequencies around 0 to pass up to a certain cutoff frequency omega c, and then it will kill the frequencies after omega c up to pi. And as you remember from the previous lecture, we've pointed out we are only interested in filters with real valued impulse response, and if h of n, the impulse response, is real valued, h of e to the power j omega is complex conjugate symmetric. In other words, the magnitude spectrum will be even and the phase spectrum will be odd, which basically means that whatever is happening from 0 to pi will be repeating from 0 to minus pi over here. So we will be having a cutoff frequency minus omega c and minus pi. And again, we are only specifying the frequency response over the interval from minus pi to pi because this is one cycle and it will be repeating, which means that the spectrum for digital filter, low pass filter, would go like this. It will be periodic, and whatever is happening at 0 will be repeating here at 2 pi, will be repeating here at minus 2 pi, and so on. Again, the discreteness in time will result in periodicity in frequency. Okay, so this is basically an ideal low-pass filter, and by ideal we mean that the pass band is flat, the gain is 1, the stop band is flat, the gain is exactly 0, and that we have a sudden transition from the pass band to stop band. This is what's meant by ideal filter. Now, this is a low-pass filter because it allows the lower frequencies to pass around 0 and kills the higher frequencies at pi and minus pi. If you remember from the supplemental video, the high frequency is happening at odd multiples of pi, 3 pi, 5 pi, minus 3 pi, and the low frequency is happening at even multiples of pi, at 0 and 2 pi, minus 2 pi, and so on. So this is the magnitude response of an ideal low-pass filter. What about the phase? The phase is required basically to be linear. In other words, the phase has to be a straight line, like this, going through the origin and with negative slope, and we will call the slope minus alpha. So again, the linear phase means that the phase is a linear function of omega, straight line going through the origin with slope of minus alpha. And we will know in few seconds why do we need the slope to be negative. The slope has to be negative for the filter to be causal. So let's try to write an expression for this h of e to the power j omega. So h of e to the power j omega is equal to, in the interval where omega is larger than minus omega c and less than omega c, which is this interval from minus omega c to omega c, the gain is 1 and the phase is minus alpha times omega. It's a straight line with a slope minus alpha, so the equation would be minus alpha times omega. So going over here, it will be a complex number whose gain is 1 and whose phase is minus alpha omega. So it's simply e to the negative j alpha omega. And in the interval where omega is larger than omega c and less than pi, and omega larger than minus pi and less than minus omega c, which is this interval over here from minus pi to minus omega c and from omega c to pi, the gain is 0 with a linear phase, so it's 0. So the gain over here will be simply 0. And this would be the frequency response of an ideal low-pass filter with a linear phase. So this is the frequency response of an ideal low-pass filter with linear phase. This is basically the desired frequency response. If you remember from the previous lecture, we start with a desired frequency response, and usually this desired frequency response we will not be able to achieve, so we try to find an actual impulse response that will be approximating this desired frequency response. Okay, so let's go back to our slides over here. So consider an ideal low-pass filter with a linear phase whose frequency response is given as follows: e to the power negative j omega alpha, where modulus omega is less than omega c. This is basically equivalent to saying omega is larger than minus omega c and less than omega c, and 0 otherwise. And this expression can be also equivalent to omega larger than omega c and less than pi, and omega larger than minus pi and less than minus omega c. But let me ask you a question over here. Why are we only concerning ourselves with low pass filter? What about high pass filter or band pass filter and so on? As we're going to see later on, we have some sort of transformations that can transform a low pass filter into a high pass filter or band pass filter and so on. That's why in this chapter and in the design of IIR filter, we will only be learning about low pass filters, because we have transformations that can transform a low pass filter into other types of filter. Okay, and if you remember from the introduction chapter we have and from the Z transform chapter, when we have an FIR filter, the filter coefficients are equal to the impulse response of the filter. And in order to remember that, let me go to the whiteboard over here and remind you with this. When we have an FIR filter, the system equations LCCDE will go like this: y of n is equal to summation of bk times xn minus k for k going from 0 up to m. And if you remember, the LCCDE had another summation for y of n minus k. But since we are talking about FIR filters, it means we have no feedback and AK will be 0. So FIR filter simply means we have no feedback and then AK will be 0. And if you remember from the introduction chapter, this kind of system will simply look like this. The input x of n will be multiplied by a constant b0, and then it will go through a delay z to the power minus 1, and here we will get x of n minus 1, which will be multiplied by b1 and added to this one, and so on until we get to the last stage where we get x of n minus m, and it will be multiplied by bm, and it will be added to whatever we have over here. This is a block diagram of an FIR filter, and the objective of designing an FIR filter is simply to find what is the value of m and what is the values of the corresponding bk's. So let's say if m is equal to 2, you will need b0, b1, and b2. If m is 10, you will need b0, b1, b2 up to b10, and so on. So designing an FIR filter is all about finding a value for m and a value for bk that would satisfy the requirement we have, which is basically a low pass filter with this kind of frequency, with this kind of pass band ripples, with this kind of stop band ripples. The filter specification we have seen in the previous lecture. So moving on, if we try to find the impulse response of this filter, if you remember, we will simply replace x by a delta. So in order to find the impulse response will be the same equation but replacing x by a delta. So summation of bk delta of n minus k for k going from 0 up to m, which is simply b0 times delta of n plus b1 times delta of n minus 1 plus b2 delta of n minus 2 up to bm delta of n minus m. And if we try to plot this impulse response, we will be having this. This is n, and at instance 0 we will have an impulse with magnitude b0. At instant 1 we will have an impulse with magnitude b1, instant 2 b2, up to instant m with magnitude bm. So it's clear that the impulse response h of n is simply the filter coefficients, is equal to the filter coefficients b0, b1, b2, and bm. So going back to this block diagram, if you want to design a digital filter, FIR digital filter, we need to find the values for bk, and the values of bk are simply the impulse response h of n. So if we can find the impulse response h of n, we can find the filter coefficients b0, b1, b2 up to bm. So in the design of FIR filter, it's all about finding the value of m and the values of bk, and we have found that the values of bk are simply the impulse response of the filter. So going back over here, if we know the frequency response of the filter, the ideal filter we're looking for, how can we find the impulse response? If you remember, in the beginning of this lecture, we have seen that we have the so-called inverse discrete time Fourier transform, this equation over here. If we know the frequency response, h of e to the power j omega, we can use this equation in order to find the impulse response. Now that we have the impulse response, we can use this fact that the impulse response is equal actually to the coefficients b0, b1, b2, and so on in order to design our filter. Okay, so let's now try to find the impulse response of this filter we have, the ideal low-pass filter we have. So let's go back to our slides over here. We have h of e to the power j omega taking this form, e to the negative j omega alpha when modulus omega is less than omega c and 0 otherwise. So in order to find the impulse response, we will use the equation we have, h of n equal to 1 over 2 pi integration from minus pi to pi. But from minus pi up to minus omega c, it's 0. If we go to this response over here, from minus pi to minus omega c, the frequency response is 0, and from omega c to pi, the frequency response is also 0. So the integration will be only from minus omega c to omega c. So let's go back over here. So it's going from minus omega c up to omega c, and the integration will be of h of e to the power j omega, which takes the form e to the negative j alpha omega times e to the positive j omega n d omega. And now we can combine these two exponentials together, which will be 1 over 2 pi integration from minus omega c up to omega c e to the j omega n minus alpha d omega. And this integration is really straightforward. It will be 1 over 2 pi, and now since we are integrating with respect to omega, we will divide by j n minus alpha. So it will be over here j n minus alpha, and here we'll be having e to the power j omega n minus alpha, and we'll substitute from minus omega c to omega c. This will be like this, 2 pi j n minus alpha, and here we'll be having e to the power j omega c n minus alpha minus e to the negative j omega c n minus alpha. And now these two exponentials together will give us 2j sine. So moving on, we will be having h of n taking this form, 2j sine omega c n minus alpha over 2j pi n minus alpha. And again, we just used Euler equation, which describes this exponential in terms of cosine and sine, or equivalently the sine and cosine represented using the complex exponentials. So over here, the 2j will cancel out with 2j, and we'll get sine omega c n minus alpha over pi n minus alpha. So going back to our slides over here, as you can see, this is the impulse response of the ideal low-pass filter, sine omega c n minus alpha over pi n minus alpha. This equation is very important. We will use it in solving all the FIR design problems, but also it's important because it's an eye-opener. It gives us actually two important things to note. First thing is that n is going from minus infinity to positive infinity. This is the impulse response of an IIR filter, not an FIR filter. For an FIR filter, the impulse response has to be of finite duration. This is defined for time going from minus infinity to positive infinity. It's not FIR. The second thing to note is that this filter is non-causal. If you remember from the previous chapter, for a system to be causal, the impulse response has to be equal to 0 before n equals 0. Now, this impulse response has a value for n less than 0, so it's non-causal. And this is basically another problem with this impulse response. But before we move on with these two problems and seeing how we can solve them, let's try to plot this impulse response. So, moving to our whiteboard over here, this is the famous sinc function. Let me remind you of the sinc function over here. So, sinc x is equal to sine pi x over pi x. And if we try to plot this function, and here x is a continuous variable, just to make things easier, it's basically a sine wave that's basically oscillating, but now it's divided by x, the variable. So as the value of x increases, the sine wave starts to decay. So the sinc function is kind of an oscillating function, decaying as the value of x increases. Okay, what would be the value of the sinc function at x equals 0? So at x equal to 0, we have a problem, because it will give you sine 0, which is 0, over 0. So 0 over 0 is a problem. In order to solve this, we use the limits, L'Hopital rule, and it can be easily shown that sinc 0 is 1. Sinc 0 is equal to 1. So now we can plot the function. It has a value of 1 at x equal to 0, and it will be oscillating but decaying. The oscillation is happening due to the sine part of the function, this part, sine pi x, and the decaying is happening because we are dividing by x. And the 0 crossings will happen when x is equal to an integer. So at 1 and 2 and 3, and here at minus 1 and minus 2 and minus 3 and so on. It can be easily shown because sine an integer times pi is 0. Sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, and so on. That's why the 0 crossings are happening at integer values of pi. And the maximum value over here is 1. Okay, so let's move back over here to the impulse response we've got for our filter. It's sine omega c n minus alpha, where n here is a variable, over pi n minus alpha. It has the same form of a sinc function, except that we do not have a pi over here because we should have sine pi times x over pi times x. So in order to put this impulse response in the form of a sinc function, let me do it like this. It will be equal to, here we have sine and I need a pi. So I will multiply by a pi and divide by a pi. So sine pi omega c over pi times n minus alpha. And doing so, I did not change the expression. And in the denominator, I need pi times omega c over pi times n minus alpha. In order for this function to take the form of a sinc function, I need to have this kind of term. But right now, the pi is already there, n minus alpha is already there, but this term omega c over pi, I just put it over here. So in order to keep the mathematics correct, I need to multiply here in the numerator by omega c over pi. This way, this will cancel out with this and we keep the expression as is. And this basically, this part will be the sinc function we have. So the impulse response will be omega c over pi sinc omega c over pi n minus alpha. So let me write it down over here. So the impulse response of our ideal low pass filter with linear phase will be, if you go back over here, we will have omega c over pi sinc, and let's go back over here, we'll get rid of this pi, so omega c over pi n minus alpha. Omega c over pi n minus alpha, where here the variable is n. The variable here is n. Okay, so going back to the sinc function, this sinc function, it's centered around 0. But as you can see in the expression we've got for the impulse response, it's sinc omega c, which is a constant, n minus alpha, so it's kind of shifted to the right by alpha. So we have a shift. If you remember from the signals and systems course, when you have a function sine t minus 3, you're simply shifting this function to the right by 3. So now we have sinc n minus alpha, so everything will be shifted to the right by alpha. And now we will be facing a problem. What if alpha is not an integer? What if alpha is not an integer? And what if alpha is an integer? If it's an integer, it's an easy job because we will be shifting the sinc function which is a function of n now, which is integer, by integer steps. So it's easy, straightforward. But if alpha is not integer, we'll be having a problem actually. Let's go back to our slides and see how it goes. So now we have started with a ideal low pass filter with linear phase. We found the frequency response, and then we found the impulse response of this filter, and the idea here was that the filter coefficients are equal to the impulse response. So if you want to design an FIR filter, you need to find the impulse response, and these will be the filter coefficients. But now we found this form, which is a sinc function, and we have a shifted sinc function, actually shifted by an alpha. Okay, in order to understand the implication of this shifting by alpha thing, let's move to our whiteboard over here, and in order to plot this impulse response, let's do it this way. Let's plot h of n as if we have a continuous variable. So instead of using a discrete values for n, we will assume as if we have a continuous variable. And then we will sample the function we have in order to get the discrete values we're looking for. It goes like this. So we'll start by plotting a continuous function shifted at alpha, and then we will take samples of this continuous function in order to get the discreteness we have in the expression. The expression here is function of n, a discrete variable. Okay, so now if alpha is an integer, so if alpha is an integer, we will be having a sample at alpha. And as you can see over here, the sinc function is kind of a symmetric function, symmetric around this peak. If we go back over here, it's symmetric around 0, it's an even function. And if it's shifted to the right by alpha, which is an integer in this case, we will be having a sample at alpha and samples just at the integer next to alpha, before alpha and after alpha, and we will be having some sort of symmetry of samples. This sample is equal to this sample, and we're having a sample over here, sample over there, will be equal to each other. This symmetry is very important for a linear phase. And now, as we can see, if alpha is an integer, we have this symmetry intact. Now, if alpha is not an integer, this is what's going to happen. So now we'll be shifting the sinc function with the value of alpha. Again, I'll be having a continuous function over here, and then we will do the sampling. So if alpha is equal to integer plus half, so let's say 3.5 or 4.5. So during the sampling, we will not be having a sample at alpha because it's integer plus half, but we will be having a sample just after and another sample just before, and these two samples will also be symmetric. And sample after and sample, another sample before, and will be symmetric. So again, if alpha is equal to integer plus half, the symmetry is still there, and the impulse response will be symmetric. And again, this symmetry is very important for the linear phase. But now, if we have an alpha which is not an integer and which is not an integer plus half, in this case, again, the sinc function will be shifted by alpha, which is not an integer and not an integer plus half. So this alpha, and we put it like this, alpha is not equal to an integer, not equal to an integer plus half. Let me put it alpha equals, let's say 3.1, a fraction like this. So the first sample we'll be having will be at 4. And the sample before 3.1 will be at 3. So as you can see over here, these two samples are not symmetric anymore. And now we have lost the symmetry. So let's go back and say it one more time. This is very important. If alpha is an integer, let's say alpha is equal to 4. So sampling this function, we will have a sample at 4, and we will have a sample at 5, and a sample at 3, and the samples at 5 and 3 will be symmetric, will be equal to each other, because the sinc function is actually symmetric. And we will have a sample here at 6, and a sample here at 2, and these two values will also be equal to each other. We still have the symmetry in the impulse response. Here we have symmetry in the impulse response. This is happening if alpha is an integer. And again, if you go over here, if alpha is integer plus half, so let me say alpha is equal to 3.5. Now this is alpha, and we will not be having a sample at 3.5, but we will be having a sample at 4 and at 3, and these two will be also symmetric, and we'll be having a sample at 5 and 2, and these two will be symmetric, equal to each other. So here we still have symmetry in the impulse response. This symmetry is very important. But if we move on to the last case, where alpha is not an integer and not an integer plus half, so let's say it's 3.1. In this case, the samples will be at 3 and 4 are not symmetric, and the next sample here, let's say at 5, and here at 2. So again, these samples are not symmetric, so we have lost the symmetry. So here we do not have symmetry. There is no symmetry in the impulse response H of n. Okay, so let's go back to our slides and see how it goes. So there are three possible cases for alpha which affect the phase linearity as follows. If alpha is an integer, in this case the impulse response is symmetrical around the sample at n equals to alpha. So we'll be having a sample at alpha, which is an integer, and the other samples will be symmetrical around alpha. The second case, if 2 alpha is an odd integer, if 2 alpha is an odd integer, in other words, alpha is equal to integer plus half. In this case, the impulse response will be symmetrical about alpha, i.e. the samples at n equal to alpha plus half is equal to the sample at n equal alpha minus half. But there is no sample at alpha itself because alpha is not an integer, it's integer plus half. And if 2 alpha is not an integer, in this case there is no symmetry in the impulse response. Okay, and let's go forward over here and take a closer look. So this is the case for alpha equal to 6. So in alpha equal to 6, which is an integer, we'll have a sample at alpha, and the sample before and after are symmetric. So we have symmetry in the impulse response. If alpha is integer plus half, 6.5 in this case, so this is alpha, and the peak is happening at 6.5, but there is no sample at 6.5. But here we have sample at 6 and at 7. Still we have this symmetry. So in these two cases we have symmetry in the impulse response. But here if alpha is 6.25, the peak is happening at 6.25, so the sample at 6 and the sample at 7 are not equal to each other. We have lost the symmetry. This is very important. Okay, so now let's go back to our problem which we had. This impulse response we had over here is going from minus infinity to positive infinity. It's not FIR, it's not causal. So in order to address this problem, in order to create a causal FIR filter, the impulse response we've got is non-causal and not FIR. So in order to get a causal FIR filter, we can set its impulse response as follows. We will set the impulse response of our causal FIR filter to be equal to the impulse response we had before, only for the values of n from 0 up to m, and 0 elsewhere. This basically is doing this. If we have this kind of impulse response over here, which is going from minus infinity to positive infinity, this is n, and this is 0, and let's say we have, this is 1, 2, 3, 4, and let's say alpha is equal to 3. So this would be our sinc function going from minus infinity to positive infinity, and the samples will be like this: sample at 3, sample at 2, sample at 1, sample at 0, and we're having sample at minus 1, minus 2, up to minus infinity, and here sample at 4, at 5, at 6, and so on. So this part of the impulse response from 0 up to minus infinity is causing the filter to be non-causal. That's why we will get rid of this part. We will ignore it. And we will only start taking the samples from 0. And the symmetry is very important in the impulse response. So that's why we will keep samples up until we have the symmetry achieved. In other words, if we take the sample at 3, we will take a sample at 2 and at 4 because they are symmetric to each other. And the sample at 1, let's say, is symmetric with the sample at 5. So I will keep this sample and the one at 5. And the sample at 0 is symmetric with the sample at 6. So I will keep the samples up to 6. If I take the sample at n is equal to 7, I will not be having a symmetrical sample on the other side. It was at n equal to -1. But I have already got rid of this negative part. So I will only keep the impulse response from 0 up to 6. And ignore all the samples before and after or outside of this window. So let's go back over here one more time and see. So h of n, the impulse response of a causal finite impulse response filter, is simply the impulse response which was going from -infinity to positive infinity, but we will only choose the samples from 0 up to m. We ignored the samples before 0 in order to force the filter to be causal, and we will ignore the samples starting from m plus 1 up to infinity. And the value of m is determined by the symmetry in the impulse response. We need to keep the symmetry. That's why if you want to take m up to a certain point, you need to make sure that the symmetric sample, which is equal to h of m, is still there, which is h of 0. And this basically will give us a relation between m and alpha, as we're going to see later on. M should be equal to 2 alpha. So in this example over here, if we have alpha is equal to 3, m, the last sample, should be 6. And if alpha is 3.5, m should be 7, and so on. Okay, this will result in a causal FIR filter of length m plus 1, and by length here we mean the length of the impulse response. If the impulse response is going from 0 up to m, the length is m plus 1. So if 2 alpha, which is m is equal to 2 alpha, is an integer, in this case h of n is symmetrical around alpha equal to m by 2, and the resulting filter has a linear phase. There is a strong relationship between phase linearity and symmetry in the impulse response. We will not be having the time to prove it, but we need to keep in mind, if you want to have a FIR filter with linear phase, you need to keep the impulse response symmetric. So now, if we choose m equal to 2 alpha to be an integer, then the impulse response will be symmetrical about m by 2, alpha equal to m by 2. And in this case, if m is an even integer, alpha will be an integer. If m is an odd integer, then alpha will be integer plus half. And in these two cases, we'll have a symmetrical phase, symmetrical impulse response. And then we have a linear phase. But if 2 alpha is not an integer at all, in this case, the symmetry is lost, and we will have a non-linear phase response. So, to wrap things up, m should be equal to 2 alpha, and it should be chosen to be an integer. So what's m? M is the time index of the last sample in the impulse response. The impulse response will start at n equal to 0, will end up at n equal to m. M basically, if you go back to this LCCDE we had over here, this is m. This is m. This is a value of m we need to find. So now, finding this value of m, it's simply m should be equal to 2 alpha. And what's alpha? If you remember, alpha is the slope of the phase over here. So this is slope over here will determine the value of alpha, and m should be 2 alpha. If m is even, 2 alpha is an even integer, alpha is an integer, and now we have a sample at alpha and symmetrical impulse response. And if m is an odd integer, 2 alpha is an odd integer, alpha is integer plus half, and in this case we will not be having a sample at alpha, but we will have still symmetrical impulse response. So again over here, if alpha is equal to 6 means m should be equal to 12. So we will be going from 0 up to 12, which will give us a filter with length 13. We'll have a sample at 6 at alpha and symmetrical impulse response. If alpha is 6.5, so m will be 2 alpha, which is 13. So we'll be having a filter with impulse response starting from 0 ending at 13. So the length of the filter is 14. And here we will not be having a sample at alpha, but we will be having samples at alpha minus half, alpha plus half will have a symmetry. But if m is not an integer at all, 2 alpha is not an integer at all, so like in this case 6.25, in this case we will be losing the symmetry and the impulse response will not be symmetric, the phase response will not be linear. So now we can understand why we need this alpha to be an integer, integer plus half, and now we understand that the slope of the phase is not allowed to take any value. It should be only integers or integer plus half. The slope of the phase determines the shift or the delay in the time domain. Here, if alpha is equal to 6, we will have sort of a linear phase over here, and this is the so-called, it's a group delay. It's basically the differentiation or the slope of the phase. So it's kind of a constant, it's because the slope over here is the same. And if alpha is 6.5, again the slope of the phase, which is a group delay, is also a constant. But if alpha is 6.25, the slope of the phase is not constant anymore, which means that it's not linear. We have lost the phase linearity. The reason, the mathematical derivation of how the linearity is related to the symmetry in the impulse response is out of scope. We will not be doing it. So, if for a given value of delay alpha we choose m larger than 2 alpha, in this case the symmetry is lost because you will be having extra samples in the impulse response which does not have the corresponding symmetrical samples which were supposedly happening at negative values. In order to clarify, let's go back over here. Let's say we will take here in this case the sample at 13. The sample at 13 was symmetrical with the sample at -1. Now that we've gotten rid of all the samples before 0, we cannot include the sample at -1. That's why we cannot include the sample at 13, because these two samples at -1 and at 13 are symmetrical. So in order to keep the symmetry, I need to keep both of them. But if I kept sample at -1, I would have lost the causality. That's why I will only stop at m equal to 2 alpha. Okay, only FIR filters with linear phase are practically realizable. We cannot realize a filter whose phase is not linear. And all causal IIR filters with rational system functions have a nonlinear phase response. Because simply in an IIR filter, to be causal, the impulse response has to be 0 before 0. Before n equal to 0. That's why we for sure will be losing the symmetry in the impulse response, and hence we will not be getting a linear phase. So, depending on type of symmetry, if it's even or odd, and depending on the value of m, if it's even or odd, we will be having 4 types of FIR filters with linear phase. Type 1 FIR filter with linear phase, m is even, and h of n is equal to h of m minus n, which is basically h of 0 equal to h of m, and h of 1 equal to h of m minus 1. If you go back over here, m here is equal to 12, so h of 0 is equal to h of m, and h of 1 is equal to h of m minus 1. And h of 2 is equal to h of m minus 2. This is the kind of symmetry we're talking about. Here, it's a different situation. Here, alpha is an integer. So, over here, if m is even, m is equal to 2 alpha, which means 2 alpha is an even integer or alpha is an integer, h of n will be equal to h of m minus n. This is called type 1 FIR filter. Type 2 filter will be having the same equation, the same symmetry, but m will be odd. So if m is 13, let's say, now alpha would be 6.5. So if you go back over here, in this case, m is 13, alpha is 6.5, and h of 0 is equal to h of m, h of 13. h of 1 is equal to h of 13 minus 1. h of 2 is equal to h of m minus 2, and so on. We still have this symmetry. So keep in mind that if m is even, it's type 1 filter. If m is odd, it's type 2 filter, given we have this kind of symmetry, the even symmetry, h of n is equal to h of m minus n. But if m is even and h of n is equal to minus h of m minus n, now this is called type 3 linear phase FIR filter, and type 4 when m is odd and h of n is equal to minus h of m minus n. And in the remaining part of this chapter, we will mainly work with type 1 and type 2 FIR filters. And in the exam, I will be asking you to design type 1 filter or type 2 filter with linear phase. So keep in mind, if it's type 1, you need to keep m even. If it's type 2, you need to keep m odd. And m is equal to 2 alpha, alpha being the slope of the linear phase we need. This will be it for today's lecture. And in the next lecture, we will start talking about the procedures we can follow in order to design our FIR filter with linear phase.